So the electromagnetic spectrum is illustrated here. So we go from low energy on the left to high energy on the right. And so here is a wave, and it's just sort of drawn to represent low energy, and this looks like low energy, lethargic. And then as we go over here, the wavelength gets shorter and shorter and shorter, and this is high energy. So if you imagine this little bit here passing you at the same rate of speed as this bit over here, this is going to be high frequency, right? High frequency, short wavelength, it's high energy. This is low energy, long wavelength, low frequency. At this end, we have radio waves and then microwaves, infrared radiation. Visible light is this bit right here. Ultraviolet, X-rays, and gamma rays. Because this is so tiny on this whole scale, and because it's also so very important to us, we've taken this little piece here, pulled it down, and made it bigger. Okay, this is just a blown up part of this little tiny section. Red light is not lower in energy than microwaves. It is right in here, but that's too small for us to see conveniently. Okay? This graph gets misunderstood a lot. So if we blow this up, we see this red going through the rainbow to violet, and it always happens in that same order. The wavelength of red light is 750 nanometers. These are nanometers. And violet's 400 nanometers, and it goes in between here. Do I have the? No, I don't. And it's always in the same order. It's red, orange, well, orange, yellow, green, blue, indigo's in there somewhere, and violet. Roy G. Biv. This is why sometimes when a child draws a rainbow, you look at it and you're like, well, all the colors are there, but something's off. Because they didn't put the colors in the right order. The colors are always in that order in rainbows. Always. So if you want to draw an accurate rainbow, you got to use Roy G. Biv. You should do your best to try to remember which is more energetic, red or violet. So you remember Roy G. Biv, and this is how I finally settled on learning it. So I imagine this spectrum here, low energy to high energy, and I've got Roy G. Biv in here. And I know that ultraviolet radiation comes after violet, right? So violet's on the far right of this, and next is ultraviolet. It's like super violet, right? It's past violet. Ultraviolet is what gives me a sunburn when I go outside for more than like 15 minutes. So I try to stay in the shade. But you can get a nasty sunburn from ultraviolet radiation. It has more energy than violet light. You can't get a sunburn from visible light, but you can get a sunburn from ultraviolet. So that's how I remember that ultraviolet is more energetic than violet. And on the other side of red, the red's at this end, the other side of red is infrared. Infra is like between, below, right? So infrared radiation has less energy than red. X-rays can hurt you. Gamma rays can kill you pretty quickly. Microwaves, this one's kind of confusing because you might think, well, a microwave, that's in my microwave in my house, and then I use that to heat things up. Yes, but it's actually quite low energy. The reason it works is that it resonates with water molecules. It is a wavelength that water molecules absorb very easily. And getting the water molecules to move causes the substance to heat up. Question? Is it what? Is it damaging? There is no harm in heating food in a microwave. It does not do anything chemically to the food. It just causes the water molecules to get excited and move around. And more thermal energy is because they're moving around. And then radio waves are the lowest. So I'm going to go through these real quick because you can read about this. So gamma rays, these are produced by the sun and stars and certain unstable atomic nuclei. They are very dangerous, but they are natural. X-rays can pass through many solid substances, can be used for destroying tumors, for imaging. They have a lot of medical use, but they can also be damaging to biological molecules. So both of these can be used for good or for evil, I suppose you could say. Here's an example of how you can use radiation. This is gamma radiation. So if someone says, oh, well, they had cancer and they're having radiation therapy, right? This is one way that radiation is used. So radiation damages healthy cells and unhealthy cells. But the advantage of it is it can just go straight through. If you have a tumor in the middle of your brain, they can't cut that out because then they destroy your brain. So that's kind of defeating the purpose, right? So you can pass radiation from multiple directions with all of them focused on the tumor. So this beam is going to do some damage to the healthy tissue it goes through. But we'll do it weakly enough that it doesn't cause a lot of damage. And this beam is going to cause a little bit of damage as it goes through. And this beam is going to cause a little bit of damage as it goes through the healthy tissue. But they are all hitting the tumor. And so the tumor gets all of it, and the tumor gets damaged and hopefully destroyed. Ultraviolet, UV, stands for ultraviolet. That's what gives you a sunburn. Visible light doesn't damage biological molecules. It causes molecules in your eyes to rearrange, which gives signals to your brain, and your brain has learned to interpret that as vision. Pretty amazing. Infrared is the heat you feel from a hot object. So we heated crucibles the other day, right? And I cautioned you don't just grab them because they're hot. You put your hand next to them. If you can feel heat without touching them, it's too hot to touch. That heat that you feel coming off of a hot object is infrared. It's a form of electromagnetic radiation. All warm objects emit infrared light. Our eyes cannot see infrared light, but we can make sensors that see infrared. So using an infrared camera, you can see that this man's legs and his face and the dog's eyes and ears are warmer than like the dog's fur. And there we have proof that dogs' noses are cold. His nose is dark blue, right? So this is the normal photograph. This is infrared. We would see this even if that room was in complete darkness, no visible light, because this is just the infrared energy being given off by warm objects. This is called night vision. It's very different than actual visible light vision, but you can see warm objects even when it's completely dark. Pretty neat. Kind of already talked about that. Radio waves, that's what's used to transmit AM, FM radio. There's cell phone signals, television, different forms of communication are in that radio wave region. So then we may need to do things like this. Arrange the color of visible light, green, red, and blue, in order of increasing wavelength, frequency, and energy per photon. So how do you do this without looking at the spectrum? So this is what I do. I'd make a line here. And so I've got visible light in here. And that's going to go Roy G. Biv. And then here's violet. So next to violet must be ultraviolet. And on the other side of red is infrared, also called IR. So UV is what gives me a sunburn. This is higher in energy. So this is high energy on this end, and this is low energy. So now I've just anchored my visible spectrum there. So you don't have to do these in order. Energy per photon, the amount of energy, which light is more energetic? Green, red, or blue? Well, it's the one that's closer to ultraviolet. So there's red and green and blue. Which one's more energetic? Blue. Blue is the highest energy and red is the lowest energy. Arrange them in order of increasing. So you put the lowest first, and then the middle one, and then the highest. And as you go through that list you made, they increase. So it would be red is lower in energy than green. Green is more energetic, and blue is more energetic than green. Okay? Now if I also need a wavelength and frequency. So then I'm going to draw my little wavy picture. Okay. It doesn't need to be beautiful, just get the idea. So this high energy looking one, that's the short wavelength, right? And this is long wavelength. So if we go in order of increasing wavelength, which has the smaller wavelength, red or blue? Blue, because this end is short wavelength, this end is long. So it'd be blue, green, red. Blue is the short wavelength, green is in the middle, and red is the longest wavelength. Okay? Frequency. Well, think about standing at the beach and these waves passing. They're going at the same speed. What speed? The speed of light. So this is going to pass you less frequently, right? Because the crests are far apart, and this is going to pass more frequently. This is high frequency and low frequency. So we're supposed to go, this arrow is probably making you dizzy. It's making me dizzy. Increasing. So we want to start with low frequency. Red. So this end, this is the low frequency, so it's red, green, blue.
We can also do just like the inverse because they're opposite.
Yeah, so wavelength and frequency will end up being opposite in order. And energy and frequency will be the same. So wavelength and energy are opposite. My brain doesn't like to remember that, and so I have to, at the very least, make this picture in my head. Questions?